Hey, welcome back. So today we're going to be talking about how to draw ray diagrams for lenses, and I'm going to summarize the rules of what is positive and what is negative for curved mirrors as well as for lenses. So this is primarily for physics students in a optics unit. Sometimes that's treated as a separate unit, sometimes that is embedded into a waves unit. But yeah, we're going to continue to apply some of the concepts we have been talking about. I'll put in the description below the link for the entire playlist if you're looking for any of the related topics here. Alright, so let's go ahead and get to it. First of all, if you're dealing with a lens, you may notice in the beginning a key difference. So what do you notice that is a key difference between a lens and a mirror just at the outset? Well, one key difference between a mirror and a lens is that a lens has two focal points. And another less obvious difference from the drawing itself is that light will pass through a lens while it will reflect off of a mirror. And this may seem obvious to you, but let's state the obvious so that everyone understands what's going on. And we're going to follow the three rules that we previously talked about for drawing ray diagrams. They're going to be slightly modified here, but more or less follow the same ideas. And in a similar way that the previous rules followed the law of reflection when we talked about mirrors, here we're going to be following the concepts that we worked through before with refraction. So there's going to be a bending of light, but it will follow these three general rules. So the three rules were, if a ray comes in parallel to the optical axis, it'll go out through the focal point. Well, the question then is, which focal point are we talking about, the first one or the second one? And it really depends on what kind of a lens you have. In this case, this is a converging lens, or it's also called a double convex lens. And the ray, if it leaves the top of the image right here, you're going to have billions of rays actually, but the ones that we are interested in are going to be the ones that leave this and go parallel to the optical axis like we have right here. And then it'll go through the focal point. And because it's a converging lens, it'll go through the focal point right here. In fact, if we had another part of an object over here or something like that, it would come through and it would also go through this focal point right here. So that's what makes it a focal point, is the idea that you have parallel rays coming in and they will converge on a certain point. The second rule is, if a ray comes in through the focal point, it'll bounce out, or in this case, refracts parallel to the optical axis. So let me show you what that looks like. The ray comes in through the focal point and it goes out parallel to the optical axis. So in this case, our image is going to be inverted. It's going to be real, and we know that because if we put our hands like here, so to speak, it would interfere with the image, and it's also going to be reduced in size. And before I continue, I will show you the third rule as well. So let's go ahead and take a look at that. Third rule is, instead of if it goes through the very center of curvature of the spherical mirror, it'll bounce straight back. Here the application is, if it goes through the center of the lens, it's just going to continue straight through. And it should serve as confirmation that the image is where it belongs. Well, let's take a look at a second example here. This is also a converging lens, but notice that our object is closer to the lens than the focal point in this case, whereas previously we had the object farther away from the lens than the focal point, right? But let's follow the application of these rules that we've been talking about. So first rule is, if a ray comes in parallel to the optical axis, it'll go out through the focal point. Because it's a converging lens, it'll go through that second focal point right there. The second rule is, if it comes in through the focal point, it'll go out parallel to the optical axis. Now, we can't do that. In other words, if I drew a ray from the tip of this object here, going in this direction, it would not hit the lens. So we do the next best thing. We draw this ray as if it had gone through the focal point, so at the same angle. So let me show you what I'm talking about. That's what we're going to do. Second rule for ray diagrams for lenses is that it's going to go out parallel to the optical axis. And I do want you to notice that these are diverging rays right here, so they will never converge on the right side. So what does our brain do? Well, our brain traces the image back to see where it appears to be coming from, and where they intersect is going to be the top of the image. So let me just go ahead and show that. It would look like this. So in this case, we would describe the image as virtual because the light rays are not truly passing over here. They just are appearing to be coming from over here, upright and magnified. Oh, and if I use the third rule here, it would just go straight through. And notice again, these three rays will never converge on the right side, so you would trace that back and they would converge on the left side. Alright, let's take a look at another couple of examples here. and see how to do this. Now this is a special case right here. You won't see this very often. This may throw you for a loop, but our first rule, if it comes in parallel, it's going to go out through the focal point, fair enough. Second one we really cannot apply here. The second rule is if it comes in through the focal point, in this case it would have to go straight down, and so that's just not going to work. Let's use the third rule though here. So if it comes in through the center of the lens, it'll just continue straight through. And if I've drawn this correctly, these two rays are actually going to be parallel, which means that they are not going to intersect, either on the front or the back side of the lens. And so we would say that the image is undefined. And if you use the mirror and lens equation, they turn out to be undefined as well. So you will not have an image formed if you try to put the object right on the focal point. Alright, and the second example I want to go over is with a diverging lens where the object is farther away from the lens itself than the focal point is. So let's go ahead and draw our first ray. If it comes in parallel to the optical axis, it's now going to go out through the focal point. If this was a converging lens, it would converge. Think of it, all of these incoming parallel rays would converge at this focal point, but it's not a converging lens. It's a diverging lens, so it's going to go out as if it had come through the first focal point like this, but it's not really coming through the first focal point. It just is at the same angle as if it had come through the first focal point. The second rule is actually harder to get correct. It's tempting to say, oh, it comes in through the focal point right here and it's going to bounce out parallel, but that's not the case. In this case, what you're going to do is draw it as if it was going to hit the second focal point over here, and then it's going to refract parallel to the optical axis right here. I would say that it's actually easier just to use, for these lenses, just to use the first rule and the third rule, because the third rule is it's just going to go straight through the middle of the lens, and that can help you to guide what's happening here. Now, quick question, trick question as well, where on the right side of the lens are these three rays going to intersect? Well, the answer is nowhere, or they're diverging. They're not going to intersect. So our brain traces these lines back, and it seems as if the image is forming right here. So the image is going to be reduced, upright, and virtual in this case. Like I said, rule 1 and 3 are actually going to be easier for this kind of a diverging lens scenario to draw. Alright, what I would like to do is to summarize these positive and negative values for curved mirrors. So the key thing here that we can say is that we are almost expecting things to be on the front side of a mirror. We're going to treat those as positive. So for instance, the DI value is going to be positive if it is in front of the mirror, negative if it is in back. Oh, and before I continue, let me mention that a negative HI would mean the image would be inverted, and a magnification value of less than 1 would mean the image is reduced in size, and an M of greater than 1 would mean the image is magnified. And so now that we've reviewed our concepts for positive and negative values for curved mirrors, let's review a summary for both mirrors and lenses. So we are going to assume we have positive values, like of DI and the focal length, if they are on the front side of a mirror, and positive values of DI and F if they are on the back side of a lens. So it's almost like we expect when we're dealing with mirrors that we're going to have an image on the front side of the mirror, and when we're dealing with lenses, we're going to have an image on the back side of the lens. So if you can remember that, it'll help you to remember what's positive and what's negative in what case. So hopefully this has been helpful. If you have any comments down below, please let me know, and I hope you all have a great day. Take care.